Okay, so I'm going to code up sinusoidal embeddings. So let's start with our main function. So what am I going to do? I'm going to, okay. Say batch sizes 4 time dim is 16. And then I'm going to create a time scalar, a batched time scalar. So torch.randn b up to 1. So this is, we're going to use times between 0 and 1, just like I'm going to do in rectified flow. We're sampling t's between 0 and 1. And I want to squeeze, well, do I want to squeeze this? We'll see. So this is going to be of size B1. I think I might need to squeeze this. Well, it's already going to be on the CPU by default. Okay, so in our model, out.shape, out.shape. Okay, we're going to run this. And 4 by 1. Okay. This looks about right. So this would be by 1. Okay, so now we're going to say class sinusoidal embedding. Okay. Constructor. It's going to take in dim. So this is going to be the size of the embedding. We're going to say self.dim equals dim. I think I only need half dim, but okay. So, and then forward, self, t, okay. T dot shape is going to be B1. And okay. Okay. So, all right, we need to make this sequence of sine cosine pairs. Okay. So first we need to make this omega, right? So we need to create this list of frequencies. Okay. And so first, without the exponent, we just have a linear, we just have log of 10,000 divided into d divided by 2 minus 1 even pieces, right? So it's just the number of dimensions divided by 2, and it's 0 index, so we need a minus 1. Okay, so we're going to use linspace, right? We're going to divide log of 10,000 into d divided by 2 minus 1 even pieces, right? So that's exactly a use case for linspace. So torch.linspace start 0, end, it's going to be log math.log of 10,000, and steps, we're going to have self.dim divided by 2. And now we don't, crap, we don't just want, because that is going to give us this list, a linearly spaced list. Now we need to exponentiate it, right? Okay, so torch.exp gives us this. And we're going to call this, these are our frequencies, okay? So now that we have our frequencies, we have our omegas, okay? Now we have our omegas. T is going to be our parameter, right? That we pass in, and we need to multiply. So now we're gonna multiply T by our omegas, right? And it's gonna be batch multiplication because we have a batch of T's, right? So we do, this is, it might seem a little tricky at first, but you need to play around with it yourself. So we're gonna do T, oh yeah, I do need to make this just be, I do need to squeeze this. I need to say dot squeeze 1, and that will turn this into this. Wait. Yes, that will turn that into that. And then I'm going to do T, I'm going to broadcast, right? So B, I'm going to use this colon for B, and then I'm going to make this 1. That gives us this makes it B. Oh, I guess I could just leave it the same. Well, I like this more. It's cleaner. It's cleaner. It's cleaner. I just want to, yeah, and plus in rectified flow, I'm going to use it like this. I'm going to use it like this. So then I need to make this. So this is going to be of size, make this cleaner, say half dim. This is going to be half dim. So this is the size half dim. Okay. So we're going to say we want this to broadcast across each element in the batch, each scalar in the batch. So we're going to say this is none, right? So we have something we have T, which is going to be B1, and freaks, which is 1 half dim, is going to create something that's of dimensions B half dim, right? Because that's just how NumPy tensors work. We're going to call this args, and then we're going to, now that we have our T's multiplied by our omegas, right? We have our T's multiplied by, actually here, let's step through it so you can see. Oh. Oh. Oh, model T. Sinusoidal embedding has no attribute. Model T. Sinusoidal dims, time dim. Oh, super dot init. Okay, so let's look at this. So frequencies. So okay, let's say torch. Let's just copy this. Torch.linspace from 0 to log 10,000, where half dim is going to be equal to 8, right? That gives us this list, which is exactly what I have in my notes. So this is a linearly spaced, it's log of 10,000 linearly spaced. So it's 9.2 linearly spaced by half dim. Now we need to exponentiate this list, right? So this is x, so torch.x, x, which is exactly what I wrote here. Now, I'll just call this temp. Temp.shape is size 8, right? 16 divided by 2. Now, t.shape is 4. So t for 1 dot shape for 1, and frequencies 1 4, sorry, 1 8, sorry, not frequencies, temp 1 8. If we do t for 1 times temp 1 8, we should get something of dimensional size 4 8. Boom. That's exactly what we want. So args, so I just stepped it through twice. Args is size 4 8. Okay. So now we just need to create an embedding where we concatenate sine and cosine. But I'm not gonna keep them like paired like this. As long as they're represented in the list somewhere, it's fine, right? So all I'm gonna do is say MEEMB torch.cat torch.sine args torch.cosine args. So now the ordering, they're not consecutive pairs, but they represent the appropriate frequencies are represented by both sine and cosine in the list, and that's all that matters. Dim equals 1, right? So we're not concatenating on the batch dimension, we're concatenating on the frequency dimension. So we have 8, 8, 16. Remember, our time dimension is 16, so now we have an embedding of size 16, right? And if I were to copy and paste this here, temp 2 should be 4 by 16. Boom. So that is our time step embedding. If I run it, we get a shape of 4 by 16. Let's take a look at it. Boom. This is our time step embedding for time. For time t. So for time, so this is our time, this is our sample time. Wait, this. Yeah, right. Sorry. Okay, yeah, those are batched. And I was like, wait a minute, you can't have multiple numbers for one time. Yeah, so this is element one in the batch. Um, oh wait, randn is from a standard normal. Now this one is the max. Yeah, here you go. Wait, hold up. Here you go. Yeah, they're all between 0 and 1. Okay. Yeah. So now the time for element one in the batch is 0.3, element two is 0.7, element four is 0.5, right? And then we pass it through our sinusoidal embedding, and we should get four. We get 1, 2, 3, 4 embeddings of size 16. There you go. Sinusoidal embeddings. So just a quick review. We have batch size 4, time embedding of size 16. We sample a time step. We sample four times between 0 and 1. We define our sinusoidal embedding with the time dimension of 16. So we're going to get an embedding out of size 16. And what that does is we create a linspace. So we divide log of 10,000 into half dim equal spaces, and then we exponentiate all those spaces. And then we broadcast T and frequencies across each other. So T is of size B1, and frequencies is going to be of size 1 half dim. And wait, this is not correct. This should be a multiplication. Yeah. Okay. Frequencies is of size. Right. So we have our torch linspace where we bucket log of 10,000 into half dim equal spaces, and then we exponentiate the whole thing to get an appropriate range of magnitude for all our frequencies. We broadcast multiply T and frequencies across each other, and then we make sure that we have a unit circle for the half dim number of embedding of indexes. And that's our time step embedding. So thanks for watching. We're going to use this in the rectified flow video that I'm creating next. So stay tuned.